Hello, everyone. Welcome to the third virtual STEM fair. Thank you all for joining with us today, and I hope everyone is doing great. My name is Sri Kairanti, and I'm a rising sophomore, and I'm the organizer for this event. I wanted to bring the opportunity to other students to present and enhance their skills in STEM during this COVID-19 pandemic. We have had two great events in the past couple months, and the next fourth event is on September 26th. I have once again got amazing feedback and responses, and more events will be coming soon. See my website stemfairs.com for more details. At the end of today's fair, I will also explain how to sign up, how to be part of the next fair, and how I help the presenters through this whole process. And we have a lot of exciting topics in today's event. So let's see what they might be. The first one is gas versus electric cars. The second one is how computers work. Then introduction to physics, self-driving cars, what the universe is expanding into, and finally dark energy and matter in space. So it looks like we have some great topics for today. Also, again, check out my website stemfairs.com for information about future events. Also, remember that the event is being recorded and live streamed, and the recording of this event will be posted on my YouTube channel, STEM Explorers. So share the link uh, with with your friends and family, and remember to like and subscribe. So everyone, if you have any questions after the end of each presentation, please type them in the chat, and then I will ask them to the and then after that I will ask them to the presenters. So let's get into the presentations. First, we have Nitin. Nitin will be presenting about gas versus electric cars. So you can start presenting, Nitin.
Gas Cars versus Electric Cars by Nitin Datta Devarpalli. What are we going to talk about today in this presentation? Well, we're going to talk about how do gas cars and electric cars work, the history of a gas and electric car, challenges for both cars, which is better and why, which car is better for the environment, similarities and differences for with both types of cars. What is a gas car? Well, it is a vehicle that has an alternative fuel that uses compressed natural gas or liquefied natural gas. What is an electric car? It is a vehicle that runs by one or more electric motors using rechargeable batteries. How do gas cars work? Well, it has a battery, and the battery provides electricity to start the engine and to power the vehicle accessories. ECM, Electric Control Module. The ECM controls fuel mixture, ignition, and detects problems with the car. Exhaust system. The system channels the gases from the engine through the tailpipe. Fuel filler, a nozzle from a high pressure dispenser that attaches on the vehicle to fill the tank. Fuel injection system. This system introduces fuel to the engine's combustion chambers. Fuel line. A metal tube transfers from the tank to the engine's fuel. Fuel tank. Stores compressed natural gas on board the vehicle until it's needed by the engine. High pressure regulator reduces the pressure of the fuel exiting the tank. Internal combustion engine, an engine that generates power by the burning of a gasoline. Manual shutoff allows the vehicle operator to manually shut off. Natural gas fuel filter traps contaminants and the other products to prevent them from clogging fuel systems. Transmission. It transfers mechanical power from the engine. How do electric cars work? Has a battery that provides electricity and the other accessories, charge port, a port that connects to an external power supply to change the battery pack, DC-DC converter. It is an electrical circuit that converts high voltage from the lower voltage to run all the accessories and auxiliary battery. Electric traction motor uses power from the traction battery pack. This motor is for the wheels of the car. This is the motor that makes the wheels move also. Onboard charger. An onboard charger is built in your car. Works by converting AC power into DC energy so it can store in the battery. Power electronics controller. This unit controls the speed of the electric traction motor. It manages the electrical energy by the traction battery. Thermal system. This system keeps a proper temperature for the range of the engine, electric motor, power electronics, and other parts. Traction battery pack stores electricity by the electric traction motor. Transmission. It transfers mechanical power from the electric traction motor to drive the wheels. The history of the gas car. First, in the picture at the left is the first ever automobile known as the motor wagon, made by the German engineer at the right, Carl Benz. He patented the motor wagon, throttle system, spark plugs, gear shifters, a water radiator, a carburetor, and other components to the automobile. He is the first person to invent the car. But there are other people who were before Benz and after Benz who evolutionized and re evolutionized the automobile. First, someone before Carl Benz, in 1500s, an Italian mastermind, Leonardo da Vinci, first had an idea and started creating designs and models of transporting vehicles. Nicolas Joseph Cugna, a French inventor in 1769 who created steam, and he built the military tractor for the French army. Robert Anderson is a Scottish inventor who built the electric carriage in 1839. Gottlieb Wilhelm Daimler, a German engineer in 1886, he invented a prototype for the modern engines. Rudolf Diesel, a French inventor who patented the diesel engine. History of the electric car. William Morrison, a Scottish chemist, recreated the first ever successful electric car. But the idea of electric cars came from Robert Anderson, who first developed the first electric car. In the 1970s, electric cars became more experimental. When William Morrison created the electric wagon, people started to get interested by the idea of electric cars. When electric cars got popular, people wanted to make it better. So, for an example, Thomas Edison thought the electric cars are a great way of transportation, so he decided to create a better battery. Ferdinand Porsche creates the first ever hybrid electric car. This vehicle is powered by electricity, a gas engine, and a battery. In but in 1935, both better roads, the Texas crude oil will help, but they decline electric cars. So all the electric cars disappeared. Then, like I said, in the 1970s, the next generation of electric cars started. Fun facts about William Morrison. He was born on August 23rd, 1855 in Scotland, United Kingdom. His background in chemistry was to help improve storage batteries. He concentrated on how to produce energy for a unit of energy for efficiency for individual battery cell. He developed very powerful storage batteries. To demonstrate his batteries, he installed 24 batteries in a normal horse-drawn carriage and installed an electric motor in the rear axle and powered them. Pros and cons for electric cars. Which car is better and why? Electric cars are better because they are number one and it's good for the environment, and EVs are more efficient than gasoline cars. Why are electric cars better? They can reduce emissions, they are energy efficient, electric cars are high performance and low maintenance, They are better for the climate, and that's it. Number one, they can reduce emissions. Emission reduction, including fuel reduction, is a big pro for an electric car because the battery for the electric car doesn't create tailpipe pollution, which is a major problem in the United States for pollution. Number two, they are energy efficient. AEVs are more efficient than gas powered vehicles. AEVs can convert up to 59 to 62% of energy into vehicle movement, but the gas powered vehicle, at the other hand, it can convert up to 17 to 21% of energy movement. No, it is better for the climate. Electric car produce more global warming emissions than an average gasoline vehicle because electric cars charge lithium ion batteries, which require a lot of materials and energy to build. Number 4. Electric cars are high performance and low maintenance. All electric cars are high performance vehicles and the motors are quiet, smooth, but the internal combustion engine require less maintenance. Also, there are cons for the electric car also. Number 1, electric cars can't travel long distance. AEVs have a shorter range than a gas-powered car. Most models are between 60 and 120 miles per charge, and the more expensive models can go up to 300 miles per charge. Gas powered vehicles average around up to 300 miles on a full tank of gas. Number 3, it takes a long time to refuel. Fueling an electric car are a big issue for getting an electric car. Charging with the level 1 and level 2 charger can take up to 8 hours. Fast charging stations will take 30 minutes to charge 80% capacity. Pros and cons for gasoline cars. Pros. Gas cars can travel long distance. Gas cars can have a range of 300 to 400 miles. But on the other hand, electric cars can go up to 150 miles. And you have to charge them at the gas station will take less time. They cost less. There are so many gas cars that are very cheap than an electric car. Electric cars are expensive and the battery for the electric car is expensive also because at some point you have to change it. Cons. Tanks. Like gasoline, you need storage tanks for your car, but tanks for a natural gas car can't be installed is because you wouldn't have enough trunk space. Number 2, emissions. Gas cars have a lot of emissions and air pollutants. Tailpipe pollution is a major problem in the United States, and the cause of the tailpipe pollution is because of gas cars. When gasoline combusts, it releases carbon dioxide, carbon monoxide, nitrogen oxides, which can start climate change. Electric cars better for the environment. Why? They reduce carbon emission and pollution. They emit less greenhouse gases and air pollutants. Another benefit is that they can improve more air quality for the city and country. Electric cars produce no carbon dioxide. 1 year of electric cars have saved us 1.5 million grams of CO2. Now, I'm going to talk about all the current electric cars that are in the shop right now and what good cars that you can buy in the future also. Number one, Tesla Model 3. It is around $40,000 in the market. So price is a very good affordable price. The EVs for the Model 3 is at least 250 miles, but the 300 plus miles is a little bit more. It has improved on the production quality for the interior for the Model 3. Number 2, 2019 Audi e-tron. The price for the Audi e-tron is at a stunning price of $75,000, and the EV range for the car is 204 miles. It is a 5-passenger luxury SUV. Also, it is roomy and very comfortable. The Audi e-tron has a better battery is because the battery runs a longer time and it can run pretty fast. Number 3, the Jaguar I-Pace. The price for the car is $70,000 and the EV range for the car is 234 miles. It has very good acceleration and responsive steering. In and out of the car, it has a very good futuristic style. Future cars. Tesla Cybertruck. The price for the car is $40,000 when the car comes out, and the EV range is incredibly 500 miles. It comes with three different versions of EV ranges: 200 miles, 300 miles, or 500 miles. It has a tri motor promising of 60 miles per hour in a time of 0.29 seconds. Lexus UX300E. This is going to be the first ever electric car for Lexus. It is going to be launching in China, and the EV range for the car is 250 miles, but the car has a 15.3 kilowatt per hour battery. BMW iX3. The iX3 price is $77,000, and the EV range is 285 miles, which more than the 300E. The battery speed is at 880 kilowatts per hour. Any questions?
Thank you, Nitin, for that amazing presentation. So now, if anyone in the audience has any questions, please type them in the chat. Let's wait one more minute and see if anyone else has any questions. Okay, it seems like no one has any questions. Thank you, Nitin, for presenting. Next, we have a presentation about how to build a computer. So now you can start presenting, Lekadvik.
Hello, I'm Advigatyam, and today we'll be talking about how computers work. There are three major aspects of this presentation: the parts, building, and resources. Before we begin, what is a computer? A computer is a device that can process, usually in binary form, and has the ability to store, retrieve, and process data. The amount of things that you could do with a computer is limitless. You can play games, call people, create code, and so much more. Computers aren't just a desktop or a laptop. A calculator, console, and phone are different types of computers. Over here we have a high-end desktop. Now, these are the fundamental parts of the computer. First, we have the CPU. The CPU is the brain, the head, and the master of the computer. Leading the way, the CPU takes control of all operations in the computer. Next, we have a graphics card, or GPU. These are the eyes of the computer. This is arguably the most important part of the computer. These create frames, CUDA cores, and the graphics. Next, we have the motherboard. The motherboard, or some people like to call it the mommy board, is the bones of the computer, holding all the parts such as storage, RAM, CPU, GPU, and some select AMD coolers. Finally, we have the RAM. Random access memory is a complicated part. It's the memory of the computer. Unlike the storage of the computer, it takes recent files and games of the SSD and displays it. The remaining parts is the power supply. This is the energy of the computer / the food and water. Next, we have the storage, which holds all the games, files, and applications. And finally, we have a case, which holds all of the computer parts. Right now, we're talking about the CPU. So, what's a CPU? Well, like how I said before, it processes. And what CPU should I get? Well, when you're buying a CPU, there's AMD and Intel. Now, AMD is meant for everything, such as editing, streaming, and gaming. Intel is meant purely for gaming. So in higher-end desktops, you will see a Core i9 for gaming. Now, when you're buying a CPU for editing and streaming, a Ryzen 5 3600 will be the best choice. In the intense market of processors, there's two companies that rule it, AMD and Intel. But AMD is the way to go. Next up, we have the graphics card. The GPU is so important that almost 40% of your budget is a graphics card. If you have the best processor in the world and had a really bad GPU, your computer would be worse than a really old laptop. Seriously. The reason for this is that the GPU controls all of the graphics, making it a huge part of the computer. Now I'm going to talk about a term called bottlenecking. Bottlenecking is when one part is super powerful and the other part is too slow to support the powerful part. Next, we have the motherboard. Don't buy a motherboard just because it has Wi-Fi and Bluetooth. Get the motherboard that fits your socket and your budget. The motherboard holds the RAM, CPU, select coolers with Ryzen, and an M.2 SSD. When buying a motherboard, make sure you get one that supports your CPU, and go to the motherboard website to see if it supports your RAM. Now, some motherboards don't support the new Ryzen 3rd Gen CPUs, so make sure you do a lot of research before buying a motherboard. Now, all motherboards don't have Wi-Fi and Bluetooth. Wi-Fi and Bluetooth are a little pricey. Now, finally, there's a couple of types of motherboards. You have the ATX motherboards, which are the normal size, mini ATX, which are like a little smaller. Then you have ITX, which are smaller than mini ATXs. And honestly, when you're getting a motherboard, you also have to choose what case you have to get because each case is different from each motherboard. Next, you have the food of the computer. If you buy a really bad power supply, say goodbye to your PC. The power supply is a part where you can't go cheap on. When buying a PC, use www.pcpartpickerlist.com to inform you on the estimated wattage, and make sure when you're buying a CPU, get an 80 plus unit. Now, what does 80 plus unit mean? Well, it means that it's certified and that it won't die out in a couple of days. Now, there's multiple types of power supplies. There's a power supply that's called a modular power supply. There's a power supply that's called a semi-modular power supply, and there's a power supply called a non-modular power supply. What's the difference? Well, let's just say that you want white cables on your computer instead of the ugly ketchup and mustard cables some people like to call it. Well, you're going to have to swap them out. But if you're getting a non-modular power supply, you can't swap out any of the cables, making it difficult to do cable management and really difficult to actually connect all the cables because there's so many. Next, you have a semi-modular power supply. This is what most people tend to buy because half of the cables are already plugged in, and if you do want to swap, you're allowed to. And finally, you have a modular power supply. You can swap all cables and it's super easy for cable management. Next, we have the storage. Hard drives aren't even that bad, just make sure you have an SSD as well. If you want your computer to turn on right away, make sure you get an SSD. If you really don't mind, hard drives are a lot cheaper and slower. When I mean slow, I mean really slow. It takes around 10 seconds to load up Windows when you're having a hard drive. I would highly recommend to get an SSD and a hard drive to hold games, and an SSD for Windows. This is my personal PC. Now, building a computer is super easy. Buying the parts is the actual hard part. Now, this is me building the computer. This is a couple of pictures I did with all RGB. Now, my personal PC has a Ryzen 7, a GTX 1660, 32 gigs of RAM, and a 500 gigabyte SSD with a 700 watt power supply and a B450 motherboard. I'm going to give you 4 basic steps to build a computer. It seems really tough, but it's actually super easy. Number 1, get the motherboard and insert the CPU and RAM into the slots. If you're getting a CPU that's with Ryzen, or AMD as I should say, you'll have some select AMD coolers. You can add that right away. Next, you want to put your motherboard into your case. After that, get out your power supply, and if you have a non-modular power supply, just put it in. If not, you have a semi-modular or a modular power supply, make sure you plug in all the wires that you need. Next, connect all the wires. After that, make sure you install the SSD in the SSD case. If you have any additional hard drives, the final step is to add all your extra parts like the GPU and your other hard drives, RGB lights, Wi-Fi adapters, and anything else that you want. Like for example, fans, like RGB fans. Now, here are some useful links that you should use. This is the website for www.pcpartpickerlist. This is a really important website. When you're building a computer, you need a proper list, and you need to check if your parts are compatible. PC Part Picker List highly helps you with that. Next, we have the YouTube channel to Bitwit. Bitwit is a really good PC builder, and he tells you what parts that you should get. Next, you have the YouTube channel to Linus Tech Tips. This is also a really important YouTube channel. He tells you good tutorials on how to build a computer. Now, you really don't want to use these links below. Now, if you ever see a tutorial that has The Verge, don't click on it because they make a bunch of mistakes in that tutorial. And if you follow that tutorial, you'll probably explode your computer. Thank you so much for listening to my presentation. Do you guys have any questions?
Thank you, Advik, for that amazing presentation. Now, if anyone has any questions, please type them in the chat. So Shravya is asking, what would your dream version of a computer do differently?
Well, my dream computer would have not one, but two graphics cards. So it could do 4K and sometimes 8K. That would be my dream computer. But computers like those are super rare to build, and because they're super expensive.
And one other person is asking, for what purpose do you use your PC? Why did you build such a high-end PC?
My PC was like a normal mid-range PC. My purpose was honestly, it was just a good experience to build a PC. I would highly recommend everyone to build a PC, and it's just a good thing to have. For example, I didn't really have a proper gaming computer, so this was also a good thing to build.
Okay. Thank you for answering all those questions. And once again, thank you for presenting. Our next presenter will be talking about physics. So, Nickel, you can start presenting.
Thank you. Um, Hello, my name is Nikhil Datta Devarapalli, and I'm a freshman here in Illinois. What will I be talking about in this presentation? The origins of physics, what is physics, the seven branches of physics, famous physicists, and jobs in physics. The origin of physics. Back we go to the ancient times and start with the Greeks. Greek civilization back then was advanced and stable for their time. The ancient Greeks believed that the universe was harmonious, perfect, and governed by elegant laws and equations, as laid down by mathematicians such as Pythagoras and Euclid. Aristotle, who now is regarded as the father of science, back then in the ancient Greeks, was the founder of physics. Aristotle was a student of Plato, who was a philosopher. Aristotle was writing his own books based on his teachings from his teacher. He wrote the first work, which refers to the line of study as physics, in the 4th century BCE. Aristotle found the system known as Aristotelian physics. He attempted to explain ideas such as motion and gravity with the theory of four elements. Aristotle believed that all matter was made up of ether, or some combination of four elements: earth, water, air, and fire. The origins of physics continued. As the theory of physics spread worldwide, scientists were still trying to understand it and use it in their work. One of those people were Aryabhatta. Aryabhatta was born in Kerala and did his studies in what is now Patna, Bihar, India. He was an astrophysicist and a mathematician. His notable discoveries was the approximation of pi, and may have come to the conclusion that pi is irrational. He also did some work in trigonometry, where he found out the area of a triangle. But his most famous finding was when he was the first person to scientifically explain the lunar and solar eclipse. What is physics? Physics is the natural science that studies matter, its motion and behavior through space and time, and the related entities of energy and force. Physics is one of the most fundamental scientific disciplines, and its main goal is to understand how the universe behaves. These are the seven branches of physics: mechanics, thermodynamics, vibrations and waves, phenomena, optics, electromagnetism, relativity, and quantum mechanics. Mechanics. This branch was invented by Sir Isaac Newton in the 17th century. The branch of applied mathematics dealing with motion and forces producing motion. Mechanics may be divided into three branches: statics, which deals with forcing acting on and in a body at rest; kinematics, which describes the possible motions of a body or system of bodies; and kinetics, which attempts to explain or predict motion that will occur in a given situation. Applied mechanics, or mechanics, is useful for creating new theories, discovering and interpreting many things in the world. Thermodynamics. Thermodynamics is a branch of physics that deals with the relationships between heat and other forms of energy. In particular, it describes how thermal energy is converted to and from other forms of energy and how it affects matter. The first law of thermodynamics states that energy can be converted from one form to another with the interaction of heat, work, and eternal energy, but it cannot be created nor destroyed under any circumstances. Vibrations and waves. Vibrations are objects and substances that oscillate repeatedly over a fixed position, repeatedly which travels through a medium. In physics, a medium is a substance or material that carries the wave. The vibration moves around from one location to another, forming a wave. Waves are a wiggle in space caused by vibration or disturbance. They have the ability to carry energy from one location to another. There are two different types of waves, transversive and longitudinal. Transversive waves are always characterized by particle motion being perpendicular to wave motion. A longitudinal wave is a wave in which particles of the medium move in a direction parallel to the direction that the wave moves. So a transversive wave is perpendicular and a longitudinal wave is parallel. Optics. Abdel Haytham discovered optics and is regarded as the father of optics. Optics is the branch of physics that studies the behavior and properties of light. Optics usually describes the behavior of visible, ultraviolet, and infrared light. This includes classical optical phenomena such as reflection, refraction, diffraction, and interference, and also studying the quantum mechanical properties of individual packets of lights known as photons. Electromagnetism. Electromagnetism is a branch of physics involving the study of the electromagnetic force, a type of physical interaction that occurs between electrically charged particles. English physicist Michael Faraday discovered in work that forms the basis of electric power generation. Conversely, a changing electric field produces a magnetic field, as the Scottish physicist James Clerk Maxwell deduced. The mathematical equations formulated by Maxwell incorporated light and wave phenomena into electromagnetism. Relativity. The theory of relativity was discovered by Albert Einstein. The theory of relativity usually encompasses two interrelated theories by Albert Einstein: special relativity and general relativity. Special relativity applies to all physical phenomena in the absence of gravity. General relativity explains the law of gravitation and its relation to other forces of nature. Albert Einstein published his findings in his book in 1916. Special relativity came first and is based on the speed of light being constant for everyone. That may seem simple enough, but it has far reaching consequences. Einstein came to this conclusion in 1905 after experimental evidence showed that the speed of light didn't change as the Earth swung around the Sun. This result was surprising to physicists because the speed of most other things depends on what direction the observer is moving. If you drive your car alongside a railroad track, a train coming at you will seem to be moving much faster than if you turned around and followed it in the same direction. Quantum mechanics. Quantum mechanics was developed in the early 20th century. German physicist Max Planck invented quantum mechanics. Quantum theory is the theoretical basis of modern physics that explains the nature and behavior of matter and energy on the atomic and subatomic level. Planck wrote a mathematical equation involving a figure to represent these individual units of energy, which he called quanta. One of the most basic consequences of quantum mechanics is that there is a wave associated with the motion of all matter, including electrons in an atom. When you take that and you bring many atoms together, all of those energies broaden out into a band of possible energies. Sir Isaac Newton. This is going to be about famous physicists. Sir Isaac Newton was an English physicist and he discovered the laws of motion. Sir Isaac Newton was an English mathematician, physicist, and astrologer. Sir Isaac Newton was born on Christmas, December 25th, 1642, in Woolsthorpe, United Kingdom. His notable discoveries were Newton's laws of physics and Newton's law of universal gravitation. He graduated Trinity College with a bachelor's degree in natural philosophy. Then he started his profession as a math professor while publishing his findings alongside. One summer day, Isaac Newton was sitting under a tree when an apple fell and hit on him in the head. Then it struck him that the thought of the power of gravity was not limited to a certain distance from Earth. Newton became very famous after publishing his findings and was made a knight by Queen Anne in 1705. He died at the age of 84 in England, and he is now known as the father of physics. Albert Einstein. Major breakthrough of relativity. He is a Nobel Prize winner and discovered the formula E equals mc squared. Albert Einstein is a German born theoretical physicist. He developed the theory of relativity. He is also known for his philosophy of science and the Manhattan Project, or starting the Manhattan Project. He also won the Nobel Prize in 1921 for his discovery of the law of the photoelectric effect. He was born on March 24th, 1879, in Ulm, Germany. When Albert Einstein discovered relativity, he then formed an equation E equals mc squared, which means energy and mass are interchangeable. They are different forms of the same thing. Albert Einstein in 1921 traveled to Columbia in Princeton to deliver several lectures based on his scientific findings and research. Einstein moved to Princeton, where he occupied an office in the university's mathematics building in the 1930s. Albert Einstein finally died in 1955 in Princeton, New Jersey. Richard Feynman. Richard Feynman was an American theoretical physicist. He won a Nobel Prize in 1965 and he invented nanotechnology. Richard Phillips Feynman was an American theoretical physicist. He was known for his work in the formulation of quantum mechanics, the theory of quantum electrodynamics, and inventing nanotechnology, and also winning the Nobel Prize in 1965 for discovering quantum electrodynamics. He was also a physicist part of the Manhattan Project. He was born on May 11th, 1918 in New York City. He soon went to MIT and became a very talented physicist. Richard Feynman soon became the youngest group leader in the theoretical division in the Manhattan Project. Feynman had described a process by which the ability to manipulate individual atoms and molecules might be developed, using one set of precise tools to build and operate another proportionally smaller set, so now down to the needed scale, which became the theory and foundation of nanotechnology. Feynman then discovered quantum electrodynamics, a quantum field theory that deals with the electromagnetic field and its interaction with electrically charged particles. Stephen Hawking. Stephen Hawking is an English theoretical physicist. He discovered black holes and he declined a knighthood from the Queen. Stephen Hawking is a English theoretical physicist and cosmologist. He was known for the discovery of black holes and Hawking radiation. Stephen Hawking was diagnosed with motor neuron syndrome at the age of 21. He shook the science world in 1974 when he discovered black holes. Though he never made though he never won a Nobel Prize, he still made huge accomplishments in the science world, as Hawking radiation is a black body radiation that is predicted to be released by black holes. He worked in Relativity for some parts of his career. He declined a knighthood from the Queen because he does not like those titles. Now we're moving on to the next topic, jobs in physics. These four popular jobs include nuclear physicist, base salary of $111,567. Researching and developing safer or more efficient ways to generate nuclear power is one of the main responsibilities of a nuclear physicist. This is among the highest paying jobs in physics. Astrophysicist, base salary of $122,270. Astronomers use satellites and optical and space-based telescopes to study stars, planets, and galaxies. They develop and explore theories about how stars form and how planets evolve. Laser engineer, base salary $94,658. Designing, operating, and maintaining laser equipment requires a solid understanding of physics. Laser engineers are a specialized type of optical engineer. Theoretical physicist, base salary of $95,391. Theoretical physicists attempt to understand the laws governing nature, unlike practical or applied physicists. Thank you for listening to my presentation on the introduction of physics.
Thank you, Nitin. Sorry, thank you, Nicole, for that amazing presentation. Our next presenter, Tanvishay, she will be presenting about self-driving cars. So you can start presenting.
I'm going to put my Google slide now.
Sounds good.
Self Self-driving cars. Hi, my name is Tanasai Karmsteady and I'm going to 6th grade. This is what my presentation is going to be all about. The table of contents are: how do they work? How does the technology work? Which cars have self-driving features? Impacts. Using cell phone for self-driving cars. When will we have self-driving cars? What are the pros and cons of self-driving cars? Who made self-driving cars? And people's opinions on self-driving cars. How do they work? Self-driving cars make a map of their own and they observe their surroundings. They have a variety of sensors in different parts of the vehicle. They monitor the positions of other cars to avoid crashes. Video cameras inside the cars detect traffic lights, read road signs, track other vehicles, and look for pedestrians. Self-driving cars automatically know if the driver is conscious or not and take action immediately. Self-driving cars use many sensors in the car to make navigation easy. Some sensors that are used are blind spot monitoring, forward collision warning, radar, camera, LiDAR, and ultrasonic. AI is also used. How does the technology work? A self-driving car makes a map of its environment and places itself inside the car. Camera technology and LiDAR inside of the car are used to scan the surroundings. GPS and IMU inputs are used to build the map. Here are some pictures of how they work on the inside. Which cars have self-driving features? There are a lot of cars that have self-driving features. I will just name a few: Volvo, Volkswagen, Lexus, Land Rover, Lincoln, BMW, Buick, Jaguar, Jeep, Maserati, Mazda, Mercedes, Mitsubishi, and Mini. When will we have self-driving cars? A few years ago, everyone was saying that self-driving cars would come out in 2020, but it is already 2020. Now people are still not sure when we will have fully automated self-driving cars, meaning not only it working in certain situations, but the self-drive for the whole car ride. Impacts. The costs and benefits of self-driving cars is still largely hypothetical. More information is needed to fully assess how they'll impact drivers, the economy, equity, and the environmental and public health. When in the car, safety is very critical. Using smartphones for self-driving cars. Automakers are now planning to collab with companies like Google, Apple, and Amazon so that they can control the car from the touch of their smartphones. There will be apps that you can use inside of your phone to control it. Of course, there will be lots of security and safety before someone can hack or something in it. This is according to BMW researchers Matthias Traub, Alexander Meyer, and Kai L. Barbihan. Lots of people are invested in this idea. Who made self-driving cars? GM, other known as General Motors, made the first self-driving cars. In GM's 1939 exhibit, Norman Bell Getz created the first self-driving car. He made it by an electric vehicle guided by radio-controlled electromagnetic fields generated with magnetized metal spikes embedded in the roadway. What are the pros and cons of these cars anyway? Pros and cons. The pros are there's a little risk of drunk driving, but there's not a lot. Machines don't get tired. Robots have a higher attention span. There's many savings on fuel. Robots make fewer mistakes. Easier to use. Lesser accidents. The cons are there's privacy concerns, maintenance costs, technical errors, certain jobs will be affected, hacking issues, expensive technology, and greater pollution. Opinions. Some people say that they like self-driving cars. Some say they don't. As you can see in the earlier slide, there are many pros and cons. I personally like self-driving cars because I think that there are many pros. I like self-driving cars because they are useful in many different situations also. I asked my family what they think, and they said that they like self-driving cars. They said that they like self-driving cars because they are useful for many people, especially for blind and disabled people. What's your opinion? Conclusion. All in all, self-driving cars are very useful, and they may have some cons, but let's hope for the best. Thank you. Any questions?
Thank you for that amazing presentation. Now, if anyone has any questions in the audience, please type them in the chat. Let's wait one more minute and see if anyone else has any questions. Okay, thank you, Tanvishay, for presenting. You did great. Our next presenter, Shrivali, she will be talking about what the universe expands into. You can start presenting now.
Hey guys, so today I will be talking about the universe and what it's expanding into by yours truly, Shrivali Ketkar. So before I talk about what the universe is expanding into, I will be reviewing some key terms. The first key term that I will be reviewing is, of course, the universe. What is the universe? The universe is all existing matter and space considered as a whole, the cosmos. It's believed to be at least 10 billion light years in diameter, and it contains a vast number of galaxies. It has been expanding since its creation, the Big Bang. What is the Big Bang? The Big Bang is how the universe began about 13.8 billion years ago. The universe, as we know it, started as a small singularity, and then it started inflating or expanding over the next 13.8 billion to the. What's a light year? A light year is the term used to describe distance from space object. A light travels in 1 Earth year. 1 light year is about 6 trillion miles, 9 trillion kilometers. It's with 12 zeros. Whatever light that we may see from other objects in outer space is from the past, because the light that came to us or to our telescopes had to travel. For example, the light that we see from our sun is from 8 minutes ago from the past, because that light took 8 minutes to get here. We can use the same terminology with the moon. The light that we see from the moon is from 1.2 seconds ago, because that light from the moon took 1.2 seconds to get here. We also need to give deep regards to the fact that the universe has been expanding ever since the Big Bang, and at a faster rate per second. The Big Bang tells us that at some point in the distant past, the universe was hotter, denser, and expanding more rapidly than it is today. The expansion rate began large, but has been decreasing as the universe expands, because as the universe expands, its volume increases, and therefore the energy density goes down. As density drops, the expansion rate drops too. Right now, the universe is expanding at a rate of 73 kilometers per second. This means that for every additional 3.3 million light years away a galaxy is from Earth, it appears to be moving 73 kilometers faster per second because of the universe's expansion. One example would be the Pinwheel Galaxy. This galaxy is 20 million light years away from Earth. This means that the light that our telescope captured from this galaxy is light that traveled to the telescope from 20 million years ago. And so we see how the Pinwheel Galaxy was 20 million years ago, and we will never find out how it looks like right now in the present, even if we wait another 20 million years for it to get here, because the universe has been expanding. So the distance between Earth and this galaxy has grown between the 20 million years of time it took for that light to get here. So it would take longer for the light from that galaxy from the present to get to us in the distant future. We can, as I talked before, we can use the same terminology with the sun. The sun is 8.3 light minutes away from Earth, so the light we see from the sun is from 8.3 minutes. Key term, observable universe. Using the same concept, over time, the universe that can be seen from Earth would only be our local group of galaxies. Since the universe has expanded to the point where light from other galaxies cannot reach us now. The observable universe right now is about 93 billion. Since the universe is a newborn baby, stars, galaxies, and solar systems are full of light, which won't last too long in the future. We are lucky to be at this stage of the universe's time. Let's get to the real question. What is expanding into? Well, here's a model. The balloon can be a stand-in for space, and little sticky notes on the balloon are stand-ins for superclusters. And when the man blows into the balloon, space expands, and galaxies move farther apart without actually having to do any moving. Galaxies/superclusters are affected by expansion instead of solar systems and stars, because space-time expansion only affects things on a long scale. Here's another example similar to the balloon. Here's a loaf of raisin bread ready to rise in the oven. Consider the batter as space and raisins as stand-ins for galaxies, just as the last example. And with the heat from the oven, the batter expands, causing the raisins to move the same amount apart in the same amount of time. But the two examples I just showed you guys are terrible models. Here's why. Number one, both the balloon and the loaf of bread had curvature, positive curvature, even though all evidence points to the universe being a very flat, zero curvature universe. And second, both these models were representing 3D space on a 2D balloon and loaf of bread. The third reason why this is a terrible model is because in this model we have space for the balloon or loaf of bread to rise into, and a force that we know of making the balloon expand. For the loaf of bread, it's the heat of the oven, and for the balloon, it has somebody blowing into it. Well, the universe doesn't expand into something. In fact, it's expanding into everything or nothing. Meaning, if the universe expands into itself, it expands into everything, since the universe is everything. And on the other hand, nothing can be a little hard to comprehend, because even the nothing in these images is a black background. This is a more scientific model on how the universe might be expanding into itself. To explain this, Einstein's universe suggests that space could be curved, and if space could be curved, it could be curving into itself, which could show that the universe is basically expanding into itself. So if the universe is expanding into nothing, then another theory is that we are in an infinite universe, which basically means that the universe isn't expanding because it is already everything forever. So basically, no matter where we are in the universe, we will see an observable universe with us in the center, which could mean if we were able to travel beyond the observable universe, or even see past the observable universe, it would be the same thing again. So are there infinite copies of ourselves beyond our cosmic horizon? And if the universe was infinite, the Big Bang didn't happen in a smaller, denser area 13.8 billion years ago. It happened everywhere. Moving aside from the previous theories, another idea is that all universes are bubble universes, ours being one of them, are in a hyperspace, with each universe having different laws of sciences, physics, and gravity, things beyond imagination. And these bubble universes can never come in contact with each other because of the eternal inflation rate. A brain, in simplified terms, is universes with similar laws of sciences, physics, gravity, and most importantly, the same number of dimensions put together. Our universe may be in one of these brains. Both eternal inflation and brains describe a multiverse. But while universes in eternal inflation are isolated, brain universes could bump into each other, sending a large cosmic wave. But so far, we have found no such cosmic echo. I know that you and I both would love a more definite answer as to what the universe expands into. But the key to finding more answers is asking more questions, which is what I gave as my answer as to what the universe is expanding into. And as Neil deGrasse Tyson once said, the universe is under no obligation to make sense to you. And I agree. Let's just enjoy our time on this planet and let our imagination run wild with what the universe is and what it's expanding into. Thank you for watching. Oh, and any questions?
Thank you for presenting, Shrivali. Now, if anyone in the audience has any questions, please type them in the chat. We'll wait one more minute and see if anyone else has any questions.
Hello?
Okay, it seems like there are no questions. Once again, thank you, Shivali, for presenting. So I hope you all are learning something new. And you can find more details at stemfairs.com about future events and links to sign up as a presenter or as an audience member. And the next event is on September 26th. So let's continue with the event. Our next presenter will be about dark energy and matter in space. So you can start presenting, Amrita.
Sorry, my computer is having problems. Give me 1 moment to have everything show up and I'll be good to go. All right, hi, my name is Amrita Nandakumar, and I am going into 9th grade at Greenwich High School, and I will be presenting on dark matter and dark energy in space. Now, you might be wondering, are dark matter and dark energy the same thing? The answer is no, they are not the same thing. We know from our studies that the universe is approximately 68% dark energy, 27% dark matter, and 5% normal matter. And we know that dark energy is the force that causes our universe to expand. Dark matter is what makes up the rest of the universe, but it has not been directly observed by scientists due to its inability to be observed by the scientific instruments currently existing. It was first theorized by Fred Zwicky, who noticed that visible matter did not account for the matter in a specific galaxy, and it was confirmed by Vera Rubin and W. Kent Ford. We know it exists due to its effect on gravity, and it could serve as an explanation for multiple celestial phenomena. So we know that dark matter exists because of the way that it affects gravity mostly. Different galaxies interact with each other, and they interact with each other in ways that would not make sense based on the observable amount of matter in those galaxies. However, when you account for dark matter, those interactions start to make sense. It could also help us understand certain optical illusions that come up in space while we are observing the stars. When it comes to dark energy, its usage is a bit more clear. It's the cause of all expansion in the universe. If the expansion of the universe followed normal physics, the rate of acceleration would decrease over time, and the universe would start growing slower and slower. However, the universe is actually gaining speed, and dark energy is the force that propels this increase. So I'm going to talk a little bit more about dark matter. So first of all, what could dark matter be? We still don't know exactly what it is, so currently we're relying purely on theories to aid our studies. Now, one theory is exotic particles. They're particles that, if they exist, would have no effect on light but have a pull on gravity and affect the objects around them. Other scientists believe that the current laws of gravity don't apply in this situation to dark matter, and that there are multiple forms of other gravity that have their own rules. The hidden valley theory suggests that there is another world made of dark matter with little similarity to our own world. Although this sounds very far-fetched, considering that dark matter exists and is something that we don't know what it is, it shows that we actually know a lot less about the way our universe works, and this is a plausible theory. Hidden sector particles would be lighter than particles previously proposed, but they will need their own special detection methods, assuming that they exist. And WIMPs are weakly interacting massive particles that are supposedly heavier than other suggested particles,
and would therefore account for the imbalance in gravitational pull. So now let's talk a little bit about how dark matter is being studied. The main way it's currently being studied is through the Large Hadron Collider by CERN, and this collider would help create contain dark matter. And what that would allow scientists to do is be able to study the dark matter and the way it interacts with things around it and get a better sense for exactly what it is. Now, this is a particle accelerator, and it's the largest one in existence. So it has effects that could be bigger than anything we've ever seen before. The NASA Roman telescope would help with the viewing of the space that's called dark matter. And basically, it's an ultra-strong telescope that could be used to chart the effects of gravity that's caused by dark matter and help us gain a better understanding of what exactly it does. Xenon is a device located under Italy in an underwater tank, and its goal is to focus on WIMPs and finding those massive particles that have that high density. And hidden sector particles are particles that they're being searched for using underground tabletop devices that are looking into the skies to see if they can find the presence of this particle, and even within Earth and its surrounding atmosphere. And X-rays have also been a way that this has been studied. The Chandra X-ray Observatory has shown that when galaxies interact with each other, they give off signals that don't actually make sense due to the normal amount of matter in them, but dark matter would help account for that. And those X-rays are being observed and they're being charted, and so we're trying to understand better what's going on with with the dark matter in the universe. So now let's talk a little bit more about dark energy. So dark energy is associated with the vacuum of space. That's what goes in between basically everything. And it's what's causing the universe to expand. Its distribution through time and space is even, so the effect of dark energy in the universe never depletes. And at any given time, there is the same effect of dark energy. It is spread globally through the universe as a whole rather than to a specific part of the universe. So each part of the universe has it spread over rather than it being clumped up in a single area. To help you understand how dark energy works, here's a simple way of putting it. When you throw a ball up into the air, you expect it to return down into your hand. That's the way normal gravity works. However, dark energy is like throwing the ball up into the air and seeing it shoot up towards the ceiling. It keeps on propelling forward and accelerating, even though it should be coming back in. So there are a few explanations for dark energy that could possibly explain why it works the way it works. One theory that's been brought to prominence by Albert Einstein is the cosmological constant. This was Einstein's theory that there was a force opposite to gravity that causes the universe to not collapse, but it was disregarded by Einstein after it was proven that the universe was expanding. So if the universe was static and it didn't expand, gravity would cause it to collapse in on itself, and Einstein said that there must be something to balance that out. But dark energy keeps it moving out, so this could be the cosmological constant. However, Einstein was not a fan of this theory and eventually called it his greatest blunder. Another possible theory is a fifth fundamental force called quintessence, which would fill the universe like a fluid. So in addition to substances like earth, fire, water, wind, it would also be quintessence, which would be another way of saying dark energy, and that would be what would cause the expansion of the universe. Another theory is quantum theory, which is that the universe is filled with particles that continuously form and disappear. But when physicists tried to calculate how much energy this would have, they got a number that was 10,120 times big. That's 10 and then 120 zeros, just so you know how big that is. So scientists are a little bit confused as to how that would work if that was the case. Another theory is that, like with dark matter, the laws that we know of on Earth may be different in space,
and therefore they would have different applications and would need to have their own completely different set of rules. Or there might be no rules at all that govern the way that they interact. So how is dark energy being studied? The Dark Energy Survey is a 570 megapixel camera mounted on a large telescope that would take high definition photos and would help to see how the universe expands by taking photos of each stage of it, so scientists can look at the differences and see the growth of the universe. The Large Synoptic Survey Telescope is similar in its usage, but it would be 3.2 gigapixels, and they have plans to mount it soon, although it has not been mounted yet. This would have a similar function in observing the phenomena that happen in space and documenting it. The study is based on larger phenomena, both of these, such as galaxy placement and the interactions of large megastars, rather than smaller phenomena like individual planets. So they would be studying mostly big things rather than small individual things. So if you want to learn more, NASA has some great resources for their study on dark matter. CERN also has some resources regarding their Large Hadron Collider and the research that they're using that for in studying controlled dark matter. And National Geographic also has an article that gives a great basic overview of dark matter and energy and how they're currently being researched. Now, does anyone have any questions?
Thank you for presenting about this. So if anyone in the audience has any questions, please type them in the chat. We'll wait one more minute and see. Okay, it seems like there are no questions. Once again, thank you for presenting, Amrita. I hope everyone had a great time, and I hope you all learned something new. Thank you to everyone who watched on Zoom and on YouTube Live. I'm seeing many thank you notes in the chat, and I'm glad to see all of them. It was my pleasure to organize this event, and I appreciate your kind words. In the next month, there will be a fourth STEM fair on September 26th, and there are also going to be more dates coming soon. Here is a sneak peek at some of the topics which will be coming up in the future events. Black holes, the Raspberry Pi, and quantum computing. And there will be much, much more topics in the couple of months coming. And if you want to sign up as a presenter, you can go to stemfairs.com for the information and links to sign up. Currently, the slots for the September event have filled up, but there will be more coming soon, and you can sign up still. If you have not yet signed up as an audience member and want to watch future events, the sign-up information is once again at my website. Also, if you want to see my YouTube channel, STEM Explorers, I will post the event there. So if you came late or if you want to share it or watch a section again, you can do that. And during the last event, many asked me questions on how to sign up and what my process was on how I helped the presenters create their presentations through the whole process. So I thought I could answer those questions by providing some details. So first, a bit about me. I am a rising sophomore and I have been presenting since 4th grade in various SIT conferences and maker fairs. I am also on my school's VEX robotics team and I love exploring new technologies and coding and doing CAD. So why am I doing this then? Well, as I said before, I wanted to bring other students the same opportunity of presenting about STEM even during these special circumstances, and now I am organizing these events online. So now let's get into the process of signing up and how to be a presenter. So let's begin at my site, stemfairs.com. It has all the information about the event and links to sign up. So let's go to the website. So this is my website, stemfairs.com, and here you can see the homepage, and then scroll down to site content to go to sign up, and then you will be taken to a sign up page where you can sign up as a presenter. And then you can simply go through the form, and then I will contact you and I will help you choose a topic. So now back to slides. So for those who sign up as a presenter, the first step is choosing a topic. It can be any STEM related topic, and the topic has to be important to the presenter. So if they ask me for a topic, I ask them what they are passionate about and what they want to learn more about. And as I said, if you need help choosing your topic, I can guide you through that. The second step is to research about the topic. Use good sources and maybe even some different articles or scientific papers. And if a presenter has trouble starting their planning or finding additional sources, I can help you with those issues. And the third step is to make the actual Google Slides. I will send out a YouTube video in which I explain how to make proper slides for those who need that guidance and help. I also explain various things such as what slides to use for your topics or how to format it properly. I also check each presenter's slideshows multiple times, and I send them the feedback so that they can improve their slides. The presenters also practice their presentations very often. I then conduct 2 practices prior to the event. So that's basically how the presenters started choosing a topic, and then how they end up eventually presenting, like today's event. We had a great event today. Thank you everyone for attending the third virtual STEM fair. Thank you to all the presenters for presenting and making it a great event. I hope to see you all in the next event on September 26th. Bye everyone, and thanks for watching.